Okay students, yesterday in the lecture we studied different units of concentration. We saw it: normality, molarity, molarity, percentage of weight by weight, weight by volume and volume by volume. These were all the units that we studied. They are specifically used in laboratory to prepare solutions, to decide the amount of the solute that should be added in the solvent. Today we are going to study two other units that are used to indicate the concentration of the solution. Those two units that we are going to have to study one is mole fraction. Now mole fraction, it's a specific unit that is used for the properties, the study of the properties, or you can say that we can study many other characteristics or other components of it. For example, we can calculate the molar mass of an unknown substance when it is added by studying the colligative properties or by studying some other properties of the solutions. So what is mole fraction? We can say it as mole fraction. It's symbolized by, it looks X, but actually it's not X, it's a chi. But for the simplicity or for the students, we use the word X for it. Okay, it's a ratio of component, moles of the component upon total moles of the component. It's a ratio. Mole fraction is equals to moles of the component upon total moles of the solution. Now, when we want to understand this, we can say that we can calculate moles of component and upon moles of the component in the solution. We can study which component. Solution is made up of solute and solvent. So we can have it as in two components. So we can calculate individual component also. For it, it's written as moles of mole fraction of solute. That is equals to moles of solute upon moles of solute plus moles of solvent. Now, in this case, moles of solute, if I write it as in symbol small n, then we will be getting over here moles of solvent as capital N. So if I write it in the same abbreviation form, mole fraction of solute, that is equals to n upon n plus n. Similarly, mole fraction of solvent will be n upon n plus n. Right? Now, in this case, suppose we got it as mole fraction of solute, we get it as mole fraction of solvent. We want to calculate the mole fraction of solution. If I want to calculate the mole fraction of solution, then what will happen? What will be the value? Mole fraction of solution. That will be equals to, we will be getting it as mole fraction of solute plus mole fraction of solvent. Now we derive mole fraction of solute as n upon n plus n. For the solvent, we wrote it as n upon n plus n. If we find out its resultant answer, we will be getting it as an LCM n plus n. That means mole fraction of solution is always 1. So from this, we can say that mole fraction of solution is always 1. That means mole fraction of solute will be less than 1, or mole fraction of solvent will be less than 1. So while calculating the numericals, This can be helpful to you to find out what will be the mole fraction, whether your answers are right or wrong. You can decide it very easily. Right? This is the one unit. The second unit that we are going to discuss, that is related to ppm, parts per million. Now this is the particular unit that is being used generally we can say for the pollution purpose. It's a very less used for the other conditions in the laboratory or like that. Particularly you can say that when we are saying it, we are having an aquaguard at home. Water is coming in it. Then it is told that it clears the water up to this much TDS or this much quantity of salt can be remained in it, or most of the quantity of the salt is removed. Similarly, in a day-to-day life pollution, just because of the lockdown you can say that it's a clear atmosphere. Otherwise, the atmosphere was quite polluted. But that pollution, the quantity of the gases in the atmosphere were measured in the terms of ppm, that is parts per million. Now this is defined as milligram of solute dissolved in liter or kilogram of solvent. Again, we will write the definition for it. ppm is defined as milligram of solute. Milligram of solute dissolved in 1 liter, or you can say it 1 kilogram of solvent, or here we can also use the word solution, because the quantity of the solvent and solution, as we already saw it in the percentage of W by V, right? It's remaining same. So parts per million is defined as milligram of solute dissolved in a liter of solvent is known as 1 ppm. That means if for example 30 milligram of CaCO3 is dissolved in 1 liter water, that is 30 ppm. So whenever the unit is given to us in the terms of ppm, we can say that much amount of milligram in a solution. Or in other way, if I want to understand what is meant by 15 ppm. Suppose in the numerical it is given to me 15 ppm of solute. Right? So what does this 15 ppm means? It indicates 15 milligram of solute and 1 liter of solution. Right? So for the numericals, whenever the term is given, we should get the amount of solute and solvent out of it. Okay. Now, how to calculate the value? Suppose it is given to me in some other terms. It's not given to me every time in milligram. It's not given to me in the terms of liters or kilograms. Then how to calculate it? So for that is the formula for calculating the ppm. The formula that we use it as a ppm to calculate it is ppm is equals to mass of solute in grams. This is fixed. Now here when we are making a calculation, we will always take the mass in terms of grams upon
maybe volume or maybe mass of solution. It may be in terms of liter or in terms of gram into 10 raised to 6. So that will give me a calculation for ppm, parts per million. Right? These are all the units of the concentration that we are studying it. But these units of concentration, out of them, few are accurate, few are precise. Some of the units like normality, molarity, or you can say percentage of weight by volume, these are all considered to be as an accurate. The units like molarity, percentage of weight by weight, mole fraction, they are all considered to be as an precise. Now what is the difference between these two? Now let's first of all find out what is the difference between these two. We told it normality, molarity, percentage of weight by volume, percentage of volume by volume, whereas the other factor, that is molarity, then percentage of weight by weight, mole fraction or ppm. These two are different. Why they are different? These we told that they are accurate, while these, for this we wrote it as precise. Now why this difference is? Why this is told as to be accurate and not this one, and why these are precise? Precise means perfect, same, exact, precise. So they are more accurate. You can say that they are more perfect. Now why? What is the reason behind it? So if you see the formula of the normality, we wrote it as, it depends on volume. They are all, they depends, this all units depends on volume. You can see it in the formula. In the normality, it's a weight 1000 by molar mass into volume. Similarly, for molarity, we write it as weight 1000 molar mass into volume. Here, percentage of W by V means weight into 100 by volume. Again here, percentage of V by V is equals to V 100 V volume. These all the terms, they depend on volume. While if I go for the molarity, molarity we are going to get a weight 1000 by molar mass into weight of solvent. Percentage of W by W we will be writing it as weight 100 by weight of solution. Mole fraction, it's indicated as moles upon total moles. Right? So nowhere the unit of volume is there. Now why volume is being considered over here? Then in 11th we studied it. Volume is directly proportional to the temperature according to the Charles law. Volume changes, temperature changes. Volume increases, temperature increases, or we can say that temperature decreases, volume decreases. So here the volume is going to be affected by temperature. Every time we know that in the laboratory temperature cannot be fixed. So we are going to get the change in the temperature, and every time when we get the change, concentration will be changed because volume changes. And that is why these all the units are considered to be as a temperature dependent. And these all the units are considered as temperature independent. So this can be one of the question for you. Which are the temperature dependent? Which of the following is temperature independent? Which is going to affect the volume by the change in the temperature? So these are the terms that we want to remember as a part of the objective question. Let's try to do some of the numericals also based on all these formulas. No doubt, today within the lecture we won't be able to do it, all the numericals or all the terms. Let us at least try one or two. At least one or two. We will do it the rest of the unit calculations in the next lecture. No doubt, we will make it as a number of practice as well as in your worksheet. I will send you some of the questions, right, to solve them. So let us do it, but at least one or two, right? I am having it as one of the unit, give it to me, that is, let's have it as 6.90 molar solution of KOH in water contains 30% by mass of KOH. Calculate the density of KOH. Now, when we are having this numerical, it's given to 6.9 molar solution. 6.9 molar solution means what? 6.9 moles of solute in a liter of solution. 6.9 molarity of solution, solute in a liter of solution. At the same time, the another term that is given to me, 30% by mass. It indicates what? 30% by mass means 30 gram of solute in 70 gram of solvent. Now see why I did it like this. Yesterday we saw it in the lecture. By mass means what? Percentage of W by W. And when we are having it as a percentage of W by W means total is 100 grams of solution. Right? These are the two factors that are given to me. Again, it's told to me the solution is of KOH. Now, potassium hydroxide. Molar mass, that is, we know it, 39, 16, 1. 39 for potassium, 16 for hydrogen, oxygen, 1 for hydrogen. So totally you are going to get it as 56 gram per mole. We are going to get it as 56 gram per mole. And we want to calculate density. Density is equals to mass by volume. Right? We want to calculate density, that is mass by volume. And we want to calculate it for solution. KOH solution. Okay. So now in this case, 6.9 mole solution and this much by mass. Two factors are given to me. How to go for the calculation of it. So, one by one, we will now try to find out. From the first of all, molarity given to me, that is equals to weight of solute upon molar mass into 1000 by volume of solution. Substitute the value. This is 6.9. This is X. this is 56,000. Volume of solution, we will take it as 1 liter, that is 1000 ml. So you will be getting it, the amount of the solute as 6.9 into 56. This is the amount of solution. We will be getting it as this much grams of KOH. This is the amount of KOH in the solution. Using this, again, if I am having it as 1 liter of solution, it is containing this much. I want it in 100 ml, 30 grams, 70 grams. So this much volume should be how much? That we will be getting it. If I am having it as 30 grams, 70 grams of solvent, right? So 6.9 into 56, what will be the amount of the solvent? So we will get it as amount of the solvent from it. So we will get it as 6.9 into 56 into 70 by 30. Let us suppose it as A. We got it as solvent. We are having it as a solute. So then this will take it as B. So density will be getting it as D by A. Substitute the value and you will get the answer. See, make the calculations by yourself. I am putting the values. I got all the factors in it, but the calculations required, do it by yourself, because we are having it as a shortage of time. Right? Okay. Anyhow, for today, this is the first numerical that we saw it, that we are not getting it straight away as the formula we are having. But we will be also having some such type of numericals to be done. Right? Okay, we will do it in our next lecture, some other numericals also. Right? Okay, tomorrow we will meet again and we will solve some other numericals. Thank you.